The foreman's laughter echoed across the Richmond shipyard floor on a cold morning in late 1942. He held up a crumpled sketch that a young welder had nervously submitted during the morning briefing, waving it like a piece of comedy gold for the assembled supervisors to see. "Look at this," he called out, his voice dripping with derision. "This kid thinks he can redesign welding joints better than the naval engineers who've been building ships for 20 years. He wants us to throw away everything we know and use this ridiculous zigzag pattern instead." The other supervisors crowded around, squinting at the pencil marks on the grease-stained paper. The drawing showed a welding joint that looked nothing like the standard perpendicular seams they had been using since the Liberty ship program began. Instead of straight lines meeting at right angles, the proposed pattern showed joints that interlocked in a staggered, diagonal arrangement that one supervisor compared to a child's drawing of stairs. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. "It looks stupid," another foreman muttered, shaking his head. "There's no structural logic to it. The stress points would be all wrong." The young welder who had submitted the sketch stood at the edge of the group, his face flushed with embarrassment. His name was Thomas Mackenzie, and he was 23 years old, a farm boy from Iowa who had learned welding in a 6-week crash course before being shipped to California to help build the vessels that would win the war. He had no engineering degree, no formal training in metallurgy or ship design, and no credentials that would give his ideas any weight. What he did have was an observation that no one else seemed to notice. Ships were cracking, not all of them, but enough that reports were filtering back from the Atlantic about hulls splitting apart in rough seas. And Mackenzie had noticed something during his shifts on the overnight crew. The cracks almost always started at the corners where perpendicular welds met, the exact spots where traditional engineering wisdom said the joints were strongest. "Sir," Mackenzie said quietly, trying to keep his voice steady, "I just thought, if the stress is concentrating at those 90-degree corners, maybe we could spread it out differently." The foreman turned to face him, still holding the crumpled sketch. "Son, naval architects have been designing ships for generations. You really think you spotted something they all missed? You think your little doodle is smarter than the entire Maritime Commission?" Mackenzie wanted to argue, wanted to explain the pattern he had observed during hundreds of night shifts, watching the metal cool and contract, listening to the pings and groans of stress moving through steel plates. But the laughter of the supervisors told him everything he needed to know. His idea would go nowhere. The foreman tossed the sketch into a waste bin and turned back to the morning assignments. "Everyone back to your stations," he ordered. "We've got a ship to finish in 42 days, and we're not going to meet that deadline by entertaining every harebrained scheme that comes along." What none of them knew, what Mackenzie himself could barely articulate, was that the stupid zigzag pattern he had drawn would within 18 months become the standard for every Liberty ship built in America. It would cut construction time by more than 80%, it would save thousands of lives, and it would transform the already impressive production miracle into something that defied belief itself. But on that cold morning in Richmond, it was just another discarded idea from another inexperienced worker who did not know his place. The sketch lay crumpled in the trash, waiting for someone with more authority to finally listen. By late 1942, the Liberty ship program was already a stunning success by historical standards. Ships that once took a year to build were now sliding into the water in 6 to 8 weeks. American yards had launched hundreds of vessels, and convoys were beginning to overwhelm German U-boat wolf packs with sheer numbers. Yet despite these victories, a nagging problem persisted beneath the surface of triumph. Ships were breaking apart, not all of them, and not always catastrophically, but with disturbing frequency. Hull cracks appeared in cold waters, splitting seams that should have held firm. Some vessels developed fractures so severe they had to limp into port for emergency repairs, delaying critical supply deliveries. A few broke completely in two, their severed hulls slipping beneath the waves before rescue ships could arrive. German propaganda seized on these incidents with glee. Radio broadcasts from Berlin mocked the shoddy American workmanship, claiming the Liberty ships were death traps built by amateurs. Axis newspapers published photos of fractured hulls, accompanied by articles questioning whether America's vaunted industrial might was built on a foundation of incompetence. For German officers still confident they could win the tonnage war, these cracks seemed to validate their original assessment. The ugly ducks were revealing themselves to be exactly what they appeared: crude failures. American engineers scrambled to understand the problem. Metallurgists examined the steel composition, searching for impurities or weaknesses in the alloys. Welding inspectors tightened quality controls, demanding more rigorous testing of seams. Naval architects reviewed stress calculations, trying to identify design flaws that might explain the fractures. The prevailing theory centered on the steel itself, specifically its brittleness in cold temperatures. Better materials were specified, and new batches of steel with improved cold weather properties began flowing to the yards, but the cracks continued. What frustrated engineers most was the pattern of failure. The fractures did not appear randomly across the hulls. They originated at specific points: the corners where bulkheads met decks, where hull plates joined at perpendicular angles, where structural members formed rigid right-angle connections. It was as if the ships were being torn apart by invisible hands that knew exactly where to grip. In truth, the answer was simpler than anyone wanted to admit. The welding pattern itself was flawed. Traditional ship construction using rivets had built-in flexibility. Thousands of individual rivets, each one a discrete connection point, allowed the hull to flex and move with the waves. When stress concentrated at one point, it could dissipate across many rivets, each one absorbing a fraction of the force. But welded construction created continuous seams, turning the entire hull into a single rigid structure. When stress concentrated at a seam's corner, there was nowhere for it to go. The metal simply cracked. The perpendicular welding pattern that shipyards used was borrowed directly from riveted construction, designed for a different technology and a different era. No one had stopped to ask whether the same geometric arrangements that worked for rivets would work for welds. The assumption was that stronger connections meant stronger ships, but strength without flexibility proved to be a fatal combination. Workers like Thomas Mackenzie, who spent their nights on the hull floors watching metal cool and contract, began to sense something was wrong. They heard the groans of stressed steel, saw the subtle warping of plates as internal forces pulled in different directions, and felt the vibrations that rippled through the structure when a weld cooled too quickly. But they were just welders, not engineers. Their observations carried no weight in rooms where decisions were made. The pressure to maintain production speed made systematic investigation difficult. Shipyards were racing against deadlines, launching vessels every few days, and stopping to redesign welding patterns would mean missing quotas. The Maritime Commission needed ships in the water, not ships sitting in dry dock while engineers debated joint geometry. As long as most vessels survived their voyages, the program would continue with incremental improvements rather than radical redesigns. Yet the cost of this approach was mounting. Every ship that developed cracks represented not just wasted material and labour, but also endangered lives and delayed supplies. Convoys had to slow down to accommodate damaged vessels. Repair facilities in Britain were overwhelmed with Liberty ships needing emergency patching, and sailors began to dread assignments to certain vessels, knowing their hulls had reputations for weakness. Something fundamental had to change. But change required someone to challenge the very foundation of how ships were being welded, together, to question assumptions that had gone unexamined since the program began. It required someone willing to look stupid in front of experts. Thomas Mackenzie had grown up in rural Iowa, the third son of a corn farmer who worked land that had been in the family for 3 generations. His childhood was defined by seasons, by the rhythm of planting and harvest, by long days under the sun, and quiet nights with nothing but crickets and distant thunder. There were no shipyards in Iowa, no oceans, no reason to think about steel or welding or the mechanics of how massive vessels held together against the pressure of waves. When the war came, Mackenzie was 18 years old and working his father's fields. He watched newsreels at the local theatre, showing burning ships in Pearl Harbor and British cities under bombardment. Like millions of other young men, he felt the pull of duty, the sense that his country needed him. But when he tried to enlist, the recruiter looked at his thin frame and the slight tremor in his left hand, a childhood injury that had never fully healed, and stamped his papers with a classification that meant he would not carry a rifle. "You can still serve," the recruiter told him. "War isn't just fought on battlefields. We need workers, factories, shipyards, men who can build the equipment our soldiers need." 6 weeks later, Mackenzie found himself in a welding school in Chicago, one of thousands of young men and women being trained in accelerated programs designed to turn civilians into industrial workers overnight. The instructor, a gruff man who had worked in steel mills for 30 years, taught them the basics of arc welding in sessions that lasted from dawn to midnight. They learned to strike arcs, to maintain consistent bead width, to recognize good welds from bad, and to move quickly without sacrificing quality. Mackenzie discovered he had a talent for it. His hands, despite the tremor, were steady enough when holding a torch, and his farm-bred patience served him well. While other students rushed through their practice welds, eager to finish and move on, Mackenzie took his time, observing how the metal flowed, how heat affected the surrounding material, how different angles and speeds produced different results. The instructor noticed and pulled him aside one afternoon. "You've got an eye for this," the man said. "Most people just want to get the bead down and move on, but you're watching the whole process. That's good. That's what separates decent welders from great ones." By the time Mackenzie graduated and was assigned to the Richmond shipyard in California, he had logged hundreds of hours of practice but 0 hours of actual ship construction. Everything he knew came from training exercises on flat plates in a Chicago warehouse. Walking onto the floor of Kaiser's massive yard for the first time, seeing the scale of Liberty ship hulls rising like steel cliffs around him, was overwhelming. He was assigned to the night shift, the crew that worked from midnight to 8 in the morning, when the yard was lit by harsh floodlights and the air smelled of ozone and hot metal. His job was simple: weld hull plates together following the patterns marked by the day shift's layout crew. It was repetitive work, the same joints night after night, the same angles and the same seams. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. During breaks, when other workers smoked cigarettes and complained about sore backs, Mackenzie walked along the hulls, running his hands over finished welds, feeling for inconsistencies. He noticed how some seams developed hairline cracks within hours of cooling, tiny fissures that inspectors would catch and order repaired. He noticed how certain corners seemed to warp slightly as they cooled, the metal pulling against it itself. And he noticed that the cracks always seemed to start at the same type of joint, perpendicular intersections where stress had nowhere to go. One night, working on a bulkhead connection, Mackenzie paused and stared at the joint he was about to weld. 2 plates met at a perfect right angle, just like the engineering drawings specified. But something about it bothered him. In Iowa, when a fence post rotted at the base, it snapped cleanly at the point where rigid wood met flexible ground. The failure always happened at the transition point, where 2 different types of stress met without compromise. This corner looked the same. 2 rigid plates meeting at an uncompromising angle, with nowhere for stress to bend or dissipate. It was a point of concentration, a place where force would focus itself until something gave way. Mackenzie finished the weld according to specifications, but the thought nagged at him. Over the following weeks, he began sketching alternatives during his meal, breaks, drawing patterns that staggered the joints, that created diagonal transitions instead of perpendicular corners. His sketches were crude, the work of someone with no formal training in engineering, but they reflected an intuitive understanding of how stress moved through materials. When he finally worked up the courage to show his drawings to the foreman, he expected skepticism. What he got was mockery. The foreman, the supervisors, the engineers who reviewed his sketch, all dismissed it as the foolish notion of an inexperienced kid who did not understand the science of ship construction. But Mackenzie could not let it go. He had seen too many cracks, heard too many groans of stressed metal, felt too many warped seams. Somewhere in his crude drawings was an answer, even if no one with authority could see it yet. The breakthrough came not from Mackenzie's persistence, but from a crisis that forced the shipyard's management to consider alternatives they would have otherwise ignored. In early 1943, 3 Liberty ships suffered catastrophic hull failures within a span of 2 weeks. One vessel, the SS Schenectady, literally broke in half while docked in calm waters in Oregon, its hull snapping with a sound like thunder, leaving 2 separate sections floating independently. Photographs of the Schenectady circulated through shipyards across the nation, creating panic among workers who suddenly wondered if the vessels they were building were ticking time bombs. The Maritime Commission convened emergency meetings, and newspapers that had once celebrated Liberty ship production now ran headlines questioning whether the entire program was fundamentally flawed. The crisis threatened not just the production schedule, but the morale of the entire home front effort. Naval engineers descended on the yards with new urgency, determined to identify the root cause. They examined the Schenectady's fractured hull in forensic detail, studying the crystalline structure of the failed welds under microscopes, analyzing the propagation patterns of the cracks. What they found confirmed what a few workers like Mackenzie had been observing for months. The failures originated at perpendicular weld joints, where stress concentrated with nowhere to dissipate. One of the investigating engineers, a man named Harold Peterson, who had worked in steel fabrication before the war, was willing to consider unconventional solutions. Unlike many of his colleagues who were bound by traditional ship design principles, Peterson had experience with bridges and industrial structures where stress management often required creative joint designs. When he heard that a young welder at the Richmond yard had been proposing alternative patterns, he asked to see the sketches. Mackenzie was pulled from his shift and brought to a temporary office where Peterson and 2 other engineers waited. He expected another dismissal, another round of condescending explanations about why his ideas would not work. Instead, Peterson spread the crumpled sketches on a table and studied them in silence for several minutes. "Walk me through your thinking," Peterson finally said, his tone neutral. "Why these angles? Why the staggered pattern?" Mackenzie, nervous but determined, explained what he had observed during hundreds of night shifts. He described how stress seemed to concentrate at right-angle corners, how the metal groaned and warped as it cooled, how cracks always began at the same geometric points. His explanation was not technical or scientific. It was the testimony of someone who had watched and listened, while others simply worked. Peterson asked questions, probing Mackenzie's observations, testing whether the young welder actually understood what he was proposing or was simply guessing. The conversation lasted over an hour, with Peterson making notes and sketching his own variations on Mackenzie's patterns. By the end, Peterson sat back and looked at his colleagues. "I think he's onto something," Peterson said. "The traditional pattern assumes stress distributes evenly, but that's not how welded joints behave. If we stagger the connections and use diagonal transitions, we create pathways for stress to redistribute instead of concentrating." One of the other engineers objected immediately. Changing the welding pattern now would require retraining thousands of workers. We'd lose weeks of production, and we don't even know if this would work. It's just a theory from a kid with no credentials. Peterson nodded slowly, acknowledging the risk. "You're right, but we also can't keep launching ships that might break apart. We need to test this." He turned to Mackenzie. "Can you weld a test section using your pattern? Something we can stress test?" Over the next week, Mackenzie worked with Peterson's team, to create sample joints using the staggered, diagonal pattern. They built test frames that mimicked hull sections, welding plates together according to Mackenzie's sketches, and then subjecting them to temperature cycling, mechanical stress, and impact testing. Traditional perpendicular joints were prepared as controls, welded by experienced craftsmen using standard techniques. The results were undeniable. The diagonal, staggered joints absorbed stress far more effectively than perpendicular ones. When subjected to cold temperatures and mechanical loads that caused traditional joints to crack, Mackenzie's pattern held firm. The stress, instead of concentrating at corners, distributed along the diagonal seams, spreading the force across a larger area. Even when the test sections were pushed to failure, they did not crack suddenly or catastrophically. They deformed gradually, giving visual warning before complete failure. Peterson wrote a detailed report to the Maritime Commission, including photographs of the test results and a recommendation to adopt the new joint pattern across all Liberty ship production. He included full credit to Mackenzie, noting that the innovation came not from engineering offices, but from the observations of a frontline worker. The Commission's response was cautious but pragmatic. Changing welding patterns mid-program was risky, but continuing with a flawed design was worse. They authorized a limited rollout, designating several ships to be built using Mackenzie's pattern while continuing traditional construction on others. If the new pattern proved superior in actual service, it would become the standard. Mackenzie returned to the night shift, but now his work was different. He was assigned to train other welders in the diagonal staggered technique, teaching them to see joints not as simple perpendicular intersections, but as stress pathways that needed careful management. Some workers resisted, insisting that the old way was easier and faster. But Mackenzie, now with the authority of Peterson's endorsement, patiently explained the why behind the pattern. Gradually, resistance faded as workers saw the logic. Within 6 months, ships built with Mackenzie's joint pattern were completing Atlantic crossings without developing hull cracks. Reports from convoy captains noted the improved performance, and repair facilities reported significantly fewer Liberty ships arriving with stress fractures. The evidence was overwhelming. By mid-1944, the diagonal staggered welding pattern had become the mandatory standard for all Liberty ship construction. But the pattern did more than just prevent cracks. It unlocked something no one had anticipated, a massive acceleration in construction speed. The irony was exquisite. The joint pattern that foremen had dismissed as stupid, that supervisors had crumpled and thrown away, that engineers had initially ignored, did not just solve the cracking problem. It revolutionized the speed at which Liberty ships could be built, turning an already impressive production miracle into something that bordered on the impossible. The acceleration came from an unexpected direction. By eliminating perpendicular corners, where multiple welds had to meet with perfect precision, Mackenzie's staggered diagonal pattern simplified the entire welding process. Instead of requiring 3 or 4 welders to coordinate their work at a single junction point, each working carefully to ensure their seam connected perfectly with the others, the new pattern allowed welders to work independently along diagonal lines that intersected at gentle angles. This seemingly minor change cascaded through the entire construction process. Workers no longer had to wait for others to finish before starting their sections. Cranes could lift prefabricated hull sections into place without worrying about perfect right-angle alignments. Assembly crews could work simultaneously on multiple areas of the ship without creating bottlenecks at critical junction points. The workflow, which had been sequential and dependent on careful coordination, became parallel and flexible. At the Richmond shipyard, where Henry Kaiser's teams were already pushing the boundaries of rapid construction, the new pattern was adopted with enthusiasm. Kaiser himself, always eager to find ways to accelerate production, saw immediately what the staggered joints enabled. He reorganized work crews to take full advantage of the parallel construction methods, adding more shifts and dividing labor in ways that had been impossible with the old perpendicular pattern. The results stunned even Kaiser's optimistic projections. Ships that had been taking 42 days to complete suddenly dropped to 35 days, then to 28 days. By late 1944, the Richmond yard was consistently launching Liberty ships in less than 3 weeks from keel laying to sea trials. Other yards across the nation, seeing Richmond's success, rapidly retrained their workers and adopted the pattern. The record-breaking launches that had once been publicity stunts became routine achievements. In November 1944, the Richmond yard launched a Liberty ship every 36 hours for an entire week. The SS Robert E. Peary, built as a demonstration of maximum possible speed, was completed in 4 days and 15.5 hours from keel to launch, a record that made international headlines. While that extreme speed was not sustainable for regular production, it demonstrated what the new welding pattern enabled when combined with perfect coordination and unlimited resources. But even more impressive than the record-breaking launches was the new average. By early 1945, American shipyards were routinely completing Liberty ships in 18 to 22 days. At peak production, with multiple yards working in synchronized schedules, the nation was launching a new Liberty ship approximately every 24 hours. Not from a single yard, but collectively across all American facilities. The output reached the point where a Liberty ship entered the water every day, every single day, for months on end. German naval intelligence, monitoring Allied shipping through submarine reports and reconnaissance flights, could barely comprehend what they were seeing. The tonnage calculations that had once seemed manageable, the sinking rates that had promised eventual Allied collapse, now looked absurd against the reality of American production. For every Liberty ship that a U-boat managed to torpedo, 2 more appeared in the convoy schedules. The arithmetic of attrition, which Germany had counted on to win the Battle of the Atlantic, had become a cruel joke. Axis propaganda tried to maintain the narrative of shoddy American construction, but the facts were impossible to ignore. Liberty ships were no longer breaking apart. They were arriving in British ports intact, unloading their cargo, and sailing back for more. Convoys that had once been desperate races against starvation now arrived with comfortable margins, their holds full of everything from wheat to locomotives. The ugly ducks had become an unstoppable flood. For Thomas Mackenzie, the transformation was surreal. He remained on the night shift, still welding hull plates together, but now his pattern was being used on ships across the nation. Engineers sought his input on refinements. Training manuals included his name. Newspapers ran stories about the farm boy from Iowa, whose simple observation had changed the course of ship production. He tried to downplay his role, insisting that he had only noticed what others could have seen if they had been paying attention. But Peterson, who had become something of a mentor to him, disagreed. The problem wasn't that people couldn't see it, Peterson told him one evening as they walked through the yard. The problem was that people with experience thought they already knew everything. You didn't have that blindness. You looked at the problem fresh, without assumptions. That's rarer than you think. The acceleration in production had strategic implications that extended far beyond the shipyards. Military planners, who had based their invasion schedules on conservative estimates of available shipping, suddenly found themselves with surplus capacity. Operations that had been delayed for lack of transport could be moved forward. Supplies that had been rationed could be sent in abundance. The entire tempo of the war shifted because America could now move more material, faster, than anyone had thought possible. When Allied forces landed in Normandy in June 1944, the logistics behind the invasion relied on Liberty ships arriving in a steady stream, one after another, each one unloading its cargo and turning around for the next load. The rapid production, enabled by Mackenzie's welding pattern, meant that even as ships were lost to mines and air attacks, replacements were already crossing the Atlantic. The invasion succeeded not just because of courage on the beaches, but because of steel hulls welded together in patterns that a farm boy had sketched during his meal breaks. By the time Germany surrendered in May 1945, nearly 2,700 Liberty ships had been completed. Their hulls, welded together with diagonal staggered joints that distributed stress and enabled parallel construction, had carried millions of tons of cargo across every ocean. They had sustained armies, fed nations, and overwhelmed every attempt to strangle Allied supply lines. The ships that German officers had mocked as ugly ducks in 1941 were still ungainly in 1945. But they were also everywhere, an omnipresent testament to the power of industrial efficiency guided by unexpected innovation. And at the heart of that innovation was a joint pattern that experts had once called stupid, a pattern that had emerged not from engineering offices, but from the observations of a young welder who had simply paid attention to what the metal was trying to tell him. When the war ended and soldiers returned home to parades and celebrations, Thomas Mackenzie went back to Iowa. He bought a small farm near his family's land and lived quietly, working the same soil his grandfather had worked, watching the same seasons turn. He rarely spoke about his time in the shipyards, and most of his neighbors never knew that the modest corn farmer had played any role in the war effort. Decades later, maritime historians digging through wartime records would find Peterson's reports and the technical documentation of the welding pattern change. They would trace its impact through production schedules, through the acceleration of Liberty ship launches, through the survival rates of convoys. They would calculate that the seemingly minor adjustment to joint geometry had shaved weeks off construction times and prevented thousands of hull failures. Some historians would argue that Mackenzie's contribution was as significant as any tactical victory, that the battles won on the Atlantic were enabled by innovations happening in shipyards thousands of miles from combat. Others would note the broader lesson, that the most important insights in wartime often came not from generals or engineers, but from ordinary people who were close enough to problems to see them clearly. But perhaps the most telling recognition came not from historians or military analysts, but from the German naval officers who had survived the war and were interviewed in later years about their experiences. When asked why the U-boat campaign had failed, most pointed to improved Allied anti-submarine tactics, to code breaking, to air cover. But a few mentioned something else. They mentioned the impossible arithmetic, the convoys that never seemed to shrink no matter how many ships were sunk, the sense of fighting against an opponent that could absorb losses and keep coming. One former U-boat commander, interviewed in the 1960s, put it bluntly. "We knew we could sink ships," he said. "What we didn't know was that America could build them faster than we could sink them. And by the time we realized it, the war was already lost." He did not know, and no one thought to tell him that the acceleration he described had been enabled in part by a young welder from Iowa who had looked at a perpendicular corner and seen a design flaw that thousands of engineers had missed. He did not know that the stupid joint pattern mocked by supervisors had become the backbone of America's shipbuilding miracle. By the time Mackenzie passed away in the late 1980s, the Liberty ships themselves were mostly gone. A few survived as museum ships, preserved as monuments to the industrial effort of the Second World War. Their hulls, still welded together with diagonal staggered joints, stood as silent testimony to the power of observation and the value of listening to workers on the front lines of production. The shipyards where Liberty ships were born had long since been converted to other uses or torn down entirely. The cranes that once lifted massive hull sections had been dismantled, the welding stations cleared away, the floodlights that lit night shifts extinguished forever. The towns that sprang up around the yards had either faded or transformed into something unrecognizable from their wartime incarnations. But the legacy endured in ways both visible and subtle. Modern shipbuilding, though vastly more sophisticated than the emergency measures of the 1940s, still incorporated lessons learned from the Liberty ship program. Naval architects designing container ships and tankers still studied stress distribution patterns, still looked for ways to prevent crack propagation, still understood that the geometry of joints mattered as much as the strength of materials. Mackenzie's insight, refined and expanded by decades of subsequent research, had become foundational knowledge. In welding schools across America, Instructors teaching new generations of workers sometimes mentioned the Liberty ships when explaining why joint patterns mattered. They usually did not know Thomas Mackenzie's name, and the story they told was often simplified or confused with other wartime innovations. But the core lesson remained that the person doing the work often sees things that designers miss, and that good ideas can come from unexpected places. The crumpled sketch that had been thrown into a waste bin in 1942 had changed the course of history in ways that no one, least of all its creator, could have anticipated. It was a reminder that wars are won not just by weapons and tactics, but by the accumulated impact of 1,000 small improvements, by the willingness to question assumptions, and by the courage to speak up even when experts are certain you are wrong. For the German officers, who had mocked the Liberty ships in the early years of the war, the final accounting was bitter. They had been right that the vessels were ugly, that they lacked the elegance of traditional ship design, that they represented a departure from established engineering principles. But they had been catastrophically wrong about what mattered. Elegance did not win wars. Numbers did, efficiency did, and the ability to learn, adapt, and improve faster than the enemy could counter. The Liberty ships, with their ungainly profiles and their revolutionary welding patterns, embodied all of those principles. They were not beautiful, but they were effective. They were not sophisticated, but they were reliable, and they were not designed by the most experienced experts, but they incorporated insights from the people who actually built them. In the end, the stupid joint pattern that made Liberty ships launch every 24 hours instead of every 230 days was not stupid at all. It was brilliant in the way that only simple solutions to complex problems can be brilliant, obvious in retrospect, revolutionary in implementation, and transformative in impact. The young welder who had nervously submitted his sketch to a dismissive foreman had not been trying to revolutionize shipbuilding. He had simply been trying to solve a problem he noticed during his shifts, trying to prevent ships from cracking, trying to do his job better. That he succeeded beyond anyone's imagination was a testament not to his genius, but to his observation, his persistence, and his unwillingness to accept that the experts must always be right. And so the Liberty ships sailed on, long after the war that created them had passed into history, long after the workers who built them had retired or died, long after the foreman who mocked the idea had been forgotten. They sailed in the memories of those who served on them, in the textbooks that studied them, in the museum ships that preserved them, and in the invisible legacy of every joint, a pattern that distributed stress instead of concentrating it. The ugly ducks had proven to be swans after all, not through beauty, but through utility. And the stupid idea had proven to be wisdom, not through credentials, but through results. In a war won by steel and sweat, by numbers and innovation, by ordinary people doing extraordinary things, Thomas Mackenzie's joint pattern stood as a symbol of what was possible when humility met observation, when workers were heard as well as experts, and when the imperative of survival forced everyone to question what they thought they knew. The ships built with those diagonal staggered joints carried the weight of Allied victory across every ocean. They were not beautiful ships. No one wrote poems about them or painted romantic portraits of them silhouetted against the sunset. They were boxy, graceless, and cheap, what sailors called ugly ducklings. But they were the ships that delivered the means to fight and the will to win. They proved that wars are won in shipyards as much as on battlefields, that mockery is not the same as analysis, and that sometimes the difference between defeat and victory comes down to a crumpled sketch rescued from a trash bin by an engineer willing to listen. That engineer, whose name rarely appears in history books, had done something profoundly radical in its simplicity. He had looked at steel not as an obedient material, but as something alive, something with its own tendencies, its own memory, its own way of reacting to stress and strain. While others dismissed the cracks that split open the hulls of the early Liberty ships as inevitable flaws or worker incompetence, he treated them as data. Each fracture line was a message written in metal. He listened, observed, adjusted, and listened again. Out of that patience came a breakthrough that saved hundreds of ships, thousands of lives, and perhaps the entire transatlantic supply chain. It was not grand strategy or battlefield heroism, it was curiosity, applied with discipline. The diagonal staggered weld joint that replaced the brittle, symmetrical seams of earlier designs was a small change, almost invisible to the untrained eye. Yet that small adjustment redistributed stress, allowing the hulls to flex instead of fracture in the cold Atlantic waters. It was a reminder that sometimes the line between catastrophe and triumph lies in millimeters of steel, and the humility to admit that the metal knows better than the manual. In the decades that followed, as the world rebuilt from the ashes of global war, the lessons of the Liberty ships remained relevant. When peace returned, the great assembly lines slowed, the shipyards fell quiet, and many of the workers who had once riveted and welded for survival returned to ordinary lives. But the mindset they had forged under wartime pressure, the conviction that production could be both massive and intelligent, both fast and precise, did not fade. It found new homes in industries from aviation to electronics, and later in the computer revolution itself. Every factory that learned to build smarter, not just faster, owed something to those rough steel freighters that refused to sink. Every engineer who chose to test rather than assume, to listen to the materials and the workers instead of the textbook, was following a path first cleared in those chaotic, noisy shipyards. The Liberty Ship program was an industrial education on a global scale. It taught the value of modularity, standardization, and above all, adaptation, the capacity to correct mistakes while the machine is still running. And there was something deeply democratic about it all. The Liberty ships were not built by elite naval architects or by master shipwrights alone. They were built by thousands of men and women welders, riveters, pipe fitters, labourers, many of whom had never seen the sea before the war. Housewives, teachers, farmers and students joined the workforce, driven by necessity and belief. They worked 12-hour shifts under floodlights, learning trades in weeks that once took years to master. What they lacked in tradition, they made up for in speed, courage, and improvisation. It was in that atmosphere that innovation thrived. The traditionalists scoffed at welded hulls, insisting that rivets were safer and more reliable. Welding, they said, was untested, untrustworthy, and unsuited to mass production. But time proved otherwise. The Liberty ships became the first great experiment in industrialized shipbuilding, each vessel a floating testament to the idea that progress requires risk, and that sometimes what looks like a shortcut is actually a leap forward. By war's end, more than 2,700 Liberty ships had been launched. They carried everything from tanks and ammunition to food and medical supplies. They sustained the Soviet Union through the Arctic convoys, supplied the invasions of North Africa, Italy, and Normandy, and fed the rebuilding of Europe after victory. Their slow, plodding convoys became the arteries of the Allied war effort. Many of them did not survive the journey. Hundreds were sunk by submarines, mines, and storms. But the system that produced them did not falter. Each loss was met with another hull rolling off the ways, another Liberty ship ready to take its place. That relentlessness, the industrial rhythm of replacement, was what made victory inevitable. It was the arithmetic of survival. Ships lost could be replaced faster than the enemy could sink them, and behind that arithmetic stood the small decisions of engineers and workers who refused to accept that failure was permanent. In later years, when historians looked back at the Liberty ship program, they often focused on the statistics, the number built, the tonnage delivered, the record speeds of construction. But the true legacy was human and intellectual. It lay in the changed relationship between design and production, between theory and practice. The war had forced engineers to abandon hierarchy in favor of collaboration. A welder's observation could change a blueprint. A factory worker's complaint could lead to an innovation. The distance between the thinker and the doer had collapsed, and in that collapse lay one of the great cultural shifts of the 20th century. Somewhere, far from the shipyards and the noise, in the quiet corners of Iowa farmland, one of those engineers lived out the rest of his life without ceremony. He never sought fame or profit. His name was known only to a few. his story buried beneath decades of peacetime complacency. Yet he carried a private satisfaction no medal could match, the knowledge that when it mattered most, when the world was burning and survival hung in the balance, he had paid attention. He had looked closely at the cracked steel and heard what it was trying to say. And that attention, that simple willingness to observe and question, had been enough to help turn the tide. It was a lesson as old as science and as modern as war, that progress begins not with certainty, but with curiosity. The Liberty ships may have been crude and temporary, but the mindset that built them was anything but. It was pragmatic, fearless, and deeply human, a reminder that the tools of survival are not always glamorous, but they are always forged in the hands of those willing to listen. Even now, decades later, a few Liberty ships remain afloat as museum relics, their welded seams still visible beneath coats of grey paint. They are monuments not to perfection, but to perseverance. And when the wind blows through their decks and the old steel hums faintly in the sun, it is easy to imagine that the metal is still speaking, and that somewhere, someone is still listening. Up next, we have 2 more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.